And we're going to start off by discussing the fact that when we are talking about an equilibrium reaction, we're talking about a reaction that does not have a limiting reagent, as you might have previously learned about. A limiting reagent is a substance that will be completely used at some point in the reaction. It's a reactant that is completely used, therefore the reaction will come to a stopping point. Well, in an equilibrium process, the concentrations of reactants and products will become constant, but none of the concentrations will actually be zero. It's considered to be a dynamic situation, which means that it's ever changing. You can't really expect it to ever sit still, is what that means. So to accommodate that concept of there not being a limiting reagent, that concept of the concentrations eventually becoming constant yet always changing, we need to understand that equilibrium reactions are reversible reactions. When I write a reversible reaction, I use a double-headed arrow. So a reaction that I'm going to focus on for a little bit here is called the dimerization of nitrogen dioxide. If you would, as you're listening to this, take some notes so you can visualize what I'm talking about. There's a lot of stuff associated with equilibrium. This is a pretty complex topic, so just write some stuff down as I ask you to, please. That would be helpful. All right, for the dimerization of nitrogen dioxide, we have a reaction that begins with 2 moles of NO2. And that yields in a reversible reaction 1 mole of N2O4. Well, it's called the dimerization because you're taking NO2 and joining it to another NO2 so that you get N2O4. That's a reaction that will reach equilibrium and continually make N2O4 as a product, which is written on the right side, and also continually make NO2, which is a reactant. As it goes back and forth, the concentrations of NO2 and N2O4 will become constant at some point. Yet, they're really never truly constant. It's that the number of particles becoming N2O4 and the number of particles becoming NO2 end up forming at the same rate. The definition truly of equilibrium is the forward rate of reaction equals the reverse rate of reaction. I like to kind of describe it as if you have 2 doors in a room. You let someone go out of one door and a different person comes in the other door. The number of folks in the room remains the same, but you had a change. So that's not a great example, but it kind of gives you a decent idea. With this dimerization of nitrogen dioxide reaction, it's a really neat one that I like to demonstrate for my students. I can make some nitrogen dioxide actually by reacting a piece of copper with concentrated nitric acid, and I collect the nitrogen dioxide gas. Well, that nitrogen dioxide gas will, on its own, that means spontaneously, become N2O4. Well, it likes to become N2O4 more so as the temperature goes down. And I have actually a visual marker that tells me when it becomes N2O4 or when it's NO2. The way I know that is NO2 is a brown gas, and the warmer the temperature is, the browner that gas is. So that if I accelerate the reaction at a higher temperature, I'm going to get more NO2. The way you speak of that in an equilibrium sense is to say that the reaction favors the reactants. In that case, it's a kind of a different language that we're getting into here. So with this dimerization of NO2, where the 2 moles of NO2 become N2O4, if I increase the temperature, I produce more reactant. I know that's confusing, but it means that more NO2 is made. However, if I reduce the temperature, as I told you, the N2O4 will form. Well, it is actually a colorless gas. So that means that my mixture, because it's at equilibrium, I have NO2 and I have N2O4 in a sealed container, actually becomes lighter and lighter and lighter in color the lower that I get the temperature. So it's a really powerful reaction to show as far as equilibrium goes. And if you're looking at my PowerPoint, you do see a couple of still images of those reactants, that reactant and product. All right, a concept that we go through with equilibrium reactions is defining the equilibrium constant, which is written with an uppercase K. That equilibrium constant is truly defined as the rate law constant of the forward reaction divided by the rate law constant of the reverse reaction. So if you've heretofore done kinetics, you understand that to a certain extent, but I actually do not teach kinetics before I teach equilibrium, so my students don't know what I'm talking about with that statement. So for right now, we're going to say that that equilibrium constant, the uppercase K, which is never going to be confused with Kelvin, because it's just not in the same verbiage, represents a ratio of the concentrations of products to the concentrations of reactants at equilibrium. Some folks write it as an uppercase K with a subscript to the right of EQ to represent equilibrium constant. What I'd like for you to do is write down an equilibrium reaction, a hypothetical one, using uppercase letters that reads A plus B yields in a reversible reaction, that means write a double-headed arrow, C plus D. Now I want you to go back and using lowercase letters, put your number of moles next to each reactant and each product using the lowercase version of its respective letter. So getting really verbose here, lowercase a moles of uppercase A plus lowercase moles B of uppercase B yields in a reversible reaction lowercase moles of C of uppercase C and lowercase moles D of uppercase D. It gets really confusing. That's why I ask you to write it down. Okay, well, what we end up doing with that hypothetical reaction is writing what's known as the law of mass action, which is also known as an equilibrium expression or a K expression. And to do that, we are going to take the products, put them in the numerator, and the reactants and put them in the denominator. We're going to take the products and multiply them by their concentrations, which have been raised to the power of their coefficients. Again, it helps tremendously if you're looking at my PowerPoint as I go through this, so that an equilibrium constant will have a value that equals the concentration of product C raised to the lowercase c number of moles times the concentration of product D raised to the lowercase d number of moles divided by the concentration of reactant A raised to the lowercase a number of moles times the concentration of reactant B raised to the lowercase b number of moles. Now what we do with that is actually apply real reactants formulas and real numbers for those lowercase letters when we get into actual reactions. I'm just giving you what's known as a law of mass action formula. But we can write a K expression for any reversible reaction that is present. All we have to remember is we put the products in the numerator, the reactants in the denominator. We take their concentrations, raise them to the power of their coefficients, and make sure we multiply reactants by reactants in the denominator, products by products in the numerator. The brackets, by the way, represent concentration in moles per liter, unless otherwise stated, and it is only for two phases of substances, gaseous and aqueous. If you see a substance, a reactant or a product, that is liquid or solid, you will simply leave it out of your K expression. It is not zero. It's just not present. The brackets, again, have to be raised to the power of their coefficients. If we end up plugging in values for those concentrations and plugging in values for the moles, and we solve for the equilibrium constant and find that a K has a value less than 1, that is known as a small k value. And what it actually indicates is that we have little product formation. Now, if you think about that, if k is less than 1, it means that the number in the numerator is smaller than the number in the denominator. The number in the numerator, recall, is representative of the products. So that again indicates that when we have a K less than 1 or a small K value, we have very little product formation. However, if we have a K value that is greater than 100, it indicates that we have a large amount of product formation. Again, think of what's in the numerator and think of what's in the denominator. When we have a value of K that's greater than 100, we have lots of numerator and not so much denominator. And the reason I bother to mention small k and large K values is that we work problems quite differently with them. The concepts associated with each of them are a little different. So we're going to do our first equilibrium constant expression with real stuff, and I want you to write the K expression for that dimerization of nitrogen dioxide reaction that you wrote previously. And it should read K equals brackets N2O4, close your brackets, raised to the first power, divided by brackets NO2, close your brackets, raised to the second power. Now the reason that the N2O4 is raised to the first power is because it had an understood coefficient of 1. The reason the NO2 is raised to the second power is because it had a very blatant coefficient of 2. Now if I told you that the brackets represent moles per liter unless otherwise stated, then what you have is moles per liter in the numerator and moles squared per liter squared in the denominator. So think for just a minute about what the units of K will be in that example. If you have moles per liter divided by moles squared per liter squared, you should end up with liters per mole, because you ended up with 1 over mole per liter, which means we have the reciprocal of mole per liter. Okay, I'm going to give you your first equilibrium constant problem, and that is at 25 degrees Celsius, the equilibrium concentrations of NO2 and N2O4 are 0.0370 molar for the NO2 and 0.2315 molar for the N2O4. My question is, what is the value of K at this temperature? So what you're going to do is take that equilibrium expression that you just wrote, and you're going to plug in the concentrations at equilibrium that I gave you. You should have in your numerator, within brackets, 0.2315 raised to the first power, and in your denominator, within brackets, 0.037, and then outside of the brackets, squared. Remember that the brackets represent moles per liter. So when I actually solve for the value of K, rounding to 3 significant figures, I end up with a value that is 169 liters per mole. Now if you go back and think about what 169 liters per mole tells us, it's a large K value. That means it prefers to make product. Again, if you back up a little further, and you think about the fact that I told you that the NO2 gas is a dark brown, but the N2O4 gas is colorless, then at 25 degrees Celsius, that reaction likes to make more NO2 than it does back up, correct that, yes, I do make mistakes. It likes to make more N2O4 than it does NO2. Again, because the K value is 169 liters per mole, it's bigger than 100. It means that it prefers to make products, so it prefers to make N2O4 more than it prefers to make NO2. And what that means is that at 25 degrees Celsius, I'm not going to see a real dark brown color. But if I were to reduce the temperature, I would produce more NO2. My K value would actually change as I change temperature, and I would see a darker brown color. Okay, the second reaction I'd like for you to write is the synthesis of ammonia. And that reaction reads N2 plus 3 moles of H2 yields in a reversible reaction 2 moles of NH3. So I would like for you to write the K expression for that synthesis of ammonia. Again, products in the numerator, reactants in the denominator. For your K expression, you should have K equals the concentration of NH3 squared divided by the concentration of N2 to the first times the concentration of H2 cubed. Think about what your units for K will be in this example. K's units can vary. They can be pretty much anything you want to come up with, and they can even have no units, by the way. For this one, you should have come up with the units as liters squared per mole squared. So the problem I'm going to give you this time is at 300 degrees Celsius, the equilibrium concentrations in order as you read the reaction from left to right are for the N2 at equilibrium 2.59 molar, for the H2 at equilibrium 2.77 molar, and for the NH3 at equilibrium 1.82 molar. My question again is, what is the value of K at this temperature? We are going to get into much more complex problems, trust me. But go ahead and plug those into your K expression and solve for this value of K. When you plug them in, you should have K equals 1.82 squared divided by 2.59 to the first times 2.77 to the third. In solving for K to three significant figures, you should have 0.0602 liters squared per mole squared. Because that value of K is less than 1, you should recall that that indicates it prefers to make very little product. So in this case, remember my reactants are N2 and H2, and my product is ammonia. You might know that ammonia carries a rather potent odor with it. So what that means is at 300 degrees Celsius, this reaction actually does not have a very potent ammoniacal odor to it. It has the absence of odor of the N2 and H2 more so than it does the odor of ammonia. I again mention that small k and big K stuff because we have different methods of solving reactions. So one thing I want to stress to you is that I can take a reaction and reverse it so that what I've written as products are my reactants and what I've written as reactants are my products. And when I do that, you should understand that my numerator and denominator will flip. That means that K is the reciprocal of what it was with the original reaction. So if I take the dimerization of NO2 and I reverse it so that I have the decomposition of N2O4, I'd like for you to write that reaction. And that reads N2O4 yields in a reversible reaction 2 moles of NO2. Well, we had already solved for the K value of that reaction at 25 degrees Celsius for the dimerization of NO2. And we knew that it was 169 liters per mole. What I just explained to you is that if I reverse the reaction as we just did, then I simply take the reciprocal of K. So I can take 1 and divide by 169 liters per mole, or you may use your power button in your calculator and take 169 and raise it to the -1 power. And when you do so, you get 0.00592 moles per liter. Well, when I reverse that reaction, remember, now my N2O4 is the reactant and my NO2 is the product, and my K value at 25 degrees Celsius is labeled as a small k value, which means it prefers to make more reactant than it does product. Well, we prove with both methods here that the reaction at 25 degrees Celsius really likes to make the N2O4. So let's work a slightly different type of equilibrium problem. And let's say that at 25 degrees Celsius, the initial concentration of the N2O4 is 0.75 molar. My question is, what are the equilibrium concentrations of both reactant and product, which are known as species, at this temperature? Well, to go about working this, you can make an equilibrium chart, which will indicate the initial, change, and equilibrium concentrations. So let me explain to you, if you're not looking at my PowerPoint, how I want you to set that chart up. I want you to have 3 columns, and in the right 2 columns, I want you to have the concentration of N2O4 in the middle column, and then the concentration of NO2 on the far right column. I want you to have 4 rows. On your second row, I want you to have in the far left column, initial. On the third row, in the far left column, change. And on the fourth row, in the far left column, equilibrium. And now we're going to plug in what we know. From the given information, we know that the initial concentration of N2O4 is 0.75 molar. So I want you to write underneath the N2O4 concentration and to the right of initial 0.75. I didn't mention anything in the given information about the NO2. So our assumption is that it has yet to be made, which means that its initial concentration is understood to be 0. So underneath the NO2 on the initial row, write 0. Now what we have to think about here is that the reaction has to proceed. Nothing can remain at 0 and ever be at equilibrium. No one's concentration will ever be 0 when the reaction is at equilibrium. So we have to think about whose concentration will increase. Well, what that means is that the substance with the concentration of 0 initially, the NO2 in this case, will have to have an increase as its change. And if we increase products, then it naturally tells us we will decrease reactants. So your change for your N2O4 will be negative, and your change for your NO2 will be positive. Well, now we have to figure out by how much will it change. And that's where it's really important that you look at your balanced equation, because that mole-to-mole ratio really tells us by how much it will change. So what we make as an assumption is that the NO2 will increase by 2x because it has 2 as its coefficient. Because we make that assumption, we assume that the N2O4 will decrease by 1x. So I want you on your change line, reading from left to right, beneath your N2O4 on the change line to have minus x, and on your change line beneath the NO2 to have plus 2x. Again, we're making an assumption that this is what will occur. To get your equilibrium row information, all you do is combine your initial and your change lines. You're going to take 0.75 minus x for the N2O4 and 0 plus 2x, which is just 2x, for the NO2. What you do at this point, since we know what the K value is, we had solved for it previously, is plug into your K expression. Well, your K expression read K equals the concentration of NO2 squared divided by the concentration of N2O4 to the first. Now we plug in what we know, and we know that the K value at 25 degrees Celsius for this reaction is 0.00592 moles per liter. That will equal, we plug in what we know from the equilibrium line, 2x quantity squared. That means the 2x will be in brackets and the squared will be outside of the brackets. And we know from your math classes that that is very important, that the squared is outside of those brackets. And then in the denominator, you're going to have 0.75 minus x. Well, what I'm going to do is teach you something called the 5% rule. And the 5% rule tells us to assume that any amount that we have added to or subtracted from a given concentration other than 0 is so small that it's negligible. Well, the only one that I have here that did not start out at 0 is the N2O4's concentration, which was 0.75. So I'm going to subtract x from it theoretically, but what I'm saying is that the amount of x that I subtract from it is so small it's not really going to make a difference. For example, if I solve for x and let's say hypothetically I come up to find it to be 0.0001, well, in the grand scheme of things, 0.7499 is really the same thing as 0.75 for the purposes of doing this sort of chemistry. So I want you to draw a circle around minus x, and kind of kick it out with an arrow. And that really simplifies the way you solve this problem, because once you've done that, it now reads 0.00592 equals 2x quantity squared over 0.75. And that becomes a much simpler problem for you to solve. So I want you to go through the motions of solving for x with that minus x kicked out. I'll give you a minute to do that. And what you should find is that x has a value of 0.0333 moles per liter. Alrighty, well remember we kicked out the minus x that was attached to the 0.75. So what we now have to do is test the 5% rule. And in testing the 5% rule, we're asking ourselves, is what we removed less than 5% of the smaller initial value? If it is indeed smaller than 5% of that lower value, then we say our assumption was correct, that it was so small it was negligible, and we could remove it. And I'll get to what happens if it's a bad assumption in just a bit. So to test your 5% rule, and you do have to test your 5% rule if you're going to do this kicking out of any amount added to or subtracted from a given quantity that was not 0. So what I'm going to do is take the amount that I pulled out, which was 1x. So I'm going to multiply 1 by 0.0333. And I'm going to divide it by the smallest initial quantity that I was given that was not 0. And in this particular case, it was 0.75. So that means I have 0.0333 divided by 0.75, and then I'm going to make it a percentage by multiplying by 100. Well, when I do that, I get 4.44%. Since that is less than 5%, my assumption is a good assumption that when I subtract 0.0333 from 0.75, it's not going to make that much difference. Somebody in chemistry land somewhere decided to do this 5% rule stuff, and you'll be thankful for it in certain circumstances and give a heavy sigh in other circumstances, but welcome it when it does work. This is a case where it does work. So what we've just done is verified that we can accept our concentration of x as 0.0333. Now I want you to go back to your chart and realize that you said that the equilibrium concentration of N2O4 was 0.75 minus x. Well, that means it's 0.75 minus 0.0333. And I want you to solve for what that value is. You should be getting that the equilibrium concentration of N2O4 is 0.7167 molar. If you want to round that to 3 significant figures, that's fine. It would be 0.717 molar. You said in your chart that the equilibrium concentration of NO2 would be 2x. So I substitute in for x, and I have 2 times 0.0333, and that gives me 0.0666. Then I do one final thing, and that is to check my answer and see if it's pretty darn close to what my K value was. So I'm going to plug back into my equilibrium expression, my equilibrium concentrations. So I'm going to have K equals 0.0666 squared. divided by 0.717. I solve for K and I get 0.00619, which is not exactly 0.00592, the value of K we know, but it's close enough to be okay for this. Alrighty, I realize this is a long PowerPoint, but again, this is pretty complex stuff, so you feel free to take a break if you need to. The next thing I'm going to go over is a big K problem. So our next problem is at 25 degrees Celsius. The initial concentration of NO2 is 0.5 molar. We're just going to go back to the dimerization of NO2 reaction. And my question is, what are the equilibrium concentrations of both species at this temperature? And I want you to remember that K in this case had a value of 169 liters per mole. Since K is greater than 100, it's classified as a big K value or a large K value, and that means that lots of product is going to be made. But notice initially I didn't say anything about the N2O4, which means we don't have any product initially. So we translate that to mean that almost all of the initial amount of reactant will be used. But remember, it can't be all of the initial amount because nothing can be left at zero at equilibrium. So for a big K problem, you're going to have to make two charts. The first chart is called a stoichiometry chart, and the second chart is an equilibrium chart. And it just goes through the motions of your understanding what happens in this process. That's the rationale for doing two charts. Your stoichiometry chart is going to look very similar to the equilibrium chart that you made for the previous reaction. I want you to this time pay attention to the fact that your reactant is NO2 and your product is N2O4. We flip the reaction again back to what it was originally. So I again want three columns. The right two columns are going to have my reactant and product. So the middle column will have the concentration of NO2, and the rightmost column will have the concentration of N2O4. I want you again to have four rows. The second row, leftmost column, will be initial. The third row, leftmost column, will be change. And the fourth row, leftmost column, will be final. And now we're going to plug in what we know from this problem. We know that the initial concentration of the NO2 is 0.5 molar. We know that nothing was mentioned about the N2O4, so its concentration is 0 initially. When we think about the change in concentration, this is a stoichiometry chart, and our assumption at this point is that all of the reactant will be used. So what I want you to think about is, because this is a big K, this reaction is going to go all the way to the right side, and then it's going to go, uh-oh, I left myself with no reactant, so I need to turn around and make some reactant. So again, it's going to shove itself all the way to the right and make a whole bunch of product, and then it's going to turn around and make a little bit of reactant so that it can reach equilibrium. So for this stoichiometry chart, our change line is not going to have variables, it's going to have numbers, no variables. And our assumption is that the given amount of the limiting reagent, in this case it's the NO2, the only reactant that's there, will be completely used. I still reflect a mole-to-mole ratio on my change line. So for this change line, under the NO2, you should have minus 0.5. That means that all of the initial amount of NO2 is going to disappear. For the change line underneath the N2O4, we're going to have plus 0.25. Now the reason it is minus 0.5 and plus 0.25 is twofold. One, the reactant is present initially, so it has to decrease. The product is not present initially, so it has to increase. The amount by which it decreases and increases respectively is determined by the mole-to-mole ratio. So I get completely rid of my reactant NO2. But there were 2 moles of it, and there was only 1 mole of N2O4. So I only form half that amount of N2O4. My final line is the combination of my initial and change lines. So my final line underneath the NO2 should read 0.5 minus 0.5, which is 0. My final line for the N2O4 should read 0 plus 0.25, which is 0.25. I told you were going to make a stoichiometry chart and then an equilibrium chart. So now I want you to make an equilibrium chart. Again, the rightmost columns will have NO2's concentration and N2O4's concentrations respectively. The 3 rows beneath the top row will be initial, change, and equilibrium. Now the trick here is that your initial line of your equilibrium chart should read the same as your final line of your stoichiometry chart. So my initial line underneath the NO2 is 0. Underneath the N2O4, it is 0.25. Now what I've told you over and over is that we cannot be left with 0 of anything, reactant or product, at equilibrium. So we now know that the reaction is going to go, oops, I made too much product, and it's going to turn around and make a little bit of NO2. We just don't know how much that little bit is. So, in keeping with tradition, the change line of an equilibrium chart always has variables that reflect the mole-to-mole ratio. I know that the NO2's concentration has to increase because it has 0 there initially. So I will write plus 2x. It is plus 2x because there are 2 moles of it. The N2O4's concentration has to decrease for the concentration of the NO2 to increase, which means my change line underneath the N2O4 will read minus x. My equilibrium concentration is again going to be the sum of initial and change, which means for the NO2 it will be 2x, and for the N2O4 it will be 0.25 minus x. Whew, take a breath now. You're going to plug in to the K expression for this reaction, remembering that K had a value of 169 liters per mole, equals, in my numerator, I'm going to have the N2O4, which is my product. So I'm going to write in brackets 0.25 minus x. In my denominator, I'm going to have the NO2, which is my reactant. So I'm going to have in brackets 2x, and then outside of the brackets squared. So 2x quantity squared in my denominator. If we want to test the 5% rule on this, I'm going to assume that the amount of x that I subtract from 0.25 is so small that it doesn't matter. So if you draw a circle around the minus x and kick it out, your formula is much easier to maneuver, and it is 169 equals 0.25 divided by 2x quantity squared. In solving for x, I find that it is 0.0192 moles per liter. When I test the 5% rule, remember I take what I pulled out, which was 1x, and divide by the smallest initial concentration, which was 0.25. So I'm going to have 0.0192 divided by 0.25 times 100. That gives me 7.69%. So this is where you take a heavy sigh and you go, gosh, it's greater than 5%, so my assumption was bad. And that means I have to go back and put the minus x back in. So I'm going to reinsert the minus x that I pulled out, and my equation is going to read again, 169 equals 0.25 minus x divided by 2x quantity squared. So now notice it becomes a second order polynomial. Well, I don't think you really want to factor that one on your own. I think you want to make use of the quadratic equation. And you've wondered for forever, when on earth would I ever use the quadratic equation? Well, this would be a perfect time to use it. So what that means is we need to get the equation in the format of ax squared plus bx plus c equals 0. When I do that, I'm going to have it read 676x squared plus x minus 0.25 equals 0. And then I'm going to plug into the quadratic equation. Remember that you do get two values for x when you use the quadratic equation. A little reminder on the quadratic is the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. So my a value is 676, my b value is positive 1, and my c value is negative 0.25. And I plug into this nasty quadratic, and I'm going to select only one of my values. When I plug in, by the way, let's make sure you're plugging in properly. I have x equals the opposite of 1 plus or minus the square root of 1 squared minus 4 times 676 times negative 0.25, all divided by 2 times 676. When I get my two values of x, I'm going to have to choose one of them. And it's going to take you a little while to solve that quadratic most likely, so just stop the podcast, do your solving, and get your two values of x. You should get 0.0185 and negative 0.0200. Well, the way you decide which one of those values to accept is if you have a positive value and a negative value, you will always accept the positive value. The reason for that is because if you accepted the negative value, at some point you would end up with a negative concentration, and that is a no-no, never exists. If you happen to get two positive values, then you will always take the lesser of those values. Again, the rationale, if you were to have accepted the larger of those two values, you would end up with a negative concentration at some point. If you get two negative values, go back and check your quadratic because you did something wrong. Okay, so that means I accept 0.0185 as my value for x. You might recall that when we assumed that it was going to be a less than 5% change, got a value of 0.0192 moles per liter as a value of x. And granted, there's not that much difference between 0.0192 and 0.0185. But what we've just calculated is that 0.0185 is the accurate value for x. So now we go back to our equilibrium chart and we solve for the equilibrium concentrations by looking at that equilibrium line. And on that equilibrium line for the NO2, you said that it was 2x. Well, since we've accepted x as 0.0185, we will multiply that by 2 and get an equilibrium concentration for the NO2 of 0.0370 moles per liter. For the N2O4, we said the concentration at equilibrium would be 0.25 minus x. So when I take 0.25 and subtract 0.0185, I get 0.2315 moles per liter. And again, I'm going to check my answer as the last thing that I do. So I plug into my K expression, and I'm going to have in my numerator 0.2315 in brackets, divided by 0.037 in brackets, squared. I solve for K, and I get 169 liters per mole, which tells me that I was darned accurate with that value of x. Had I accepted the 0.0192 as the value of x, I would not have gotten a K that was acceptable on my check. Okay, that concludes my overview of equilibrium concepts. Now, I have practice sheets on my site, and all it takes is just practice, 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 practice. Equilibrium is a huge concept in chemistry, and I cannot stress enough just doing it over and over. You get into a rhythm as you work these, and you just have to pay attention to details, and boy, you can tell if you get one little thing off, it'll mess up the whole thing. So just be meticulous with your work, take breathers as you need them, and just Just be very cautious and get to where you absolutely love equilibrium problems, because they're a blast. Chemistry is just the highlight of your life at this point, isn't it? Alrighty, you have fun with these problems, and I'll be back later with probably some Le Chatelier principle stuff and solubility product constant stuff next. Have fun. Bye.